Hi, my name is Jason Biggs. I'm the Wolfram Language chemistry developer, part of the Wolfram Language, part of the Wolfram chemistry team. I'm here to talk to you about developments over the past years. This is a familiar talk I've given for the past few years to a progress update on the Wolfram Language chemistry. And so here, this is the version 2021. So let's move on to the next slide here. Right. No, so you'll notice the talk title was originally "What's New in Wolfram Language Chemistry," and then I saw there were lots of other talks with titles like "Progress in," and I really thought that sounded a lot better, so I changed it at the last minute. That's where we are. So let's see. So just a brief overview of what we'll do. I always like to give a little bit of a history for the chemistry in the Wolfram language, how things started and where we've ended up, and then talk about what's new now. So we've got some updates to molecule visualization. We can add atoms and bond labels to 2D and 3D graphics. And we've got some new additions to the MoleculeDraw function, which allow easy adding of hydrocarbon chains and ring structures. Then I want to talk a little bit about different chemical representations, namely the chemical formula that's new in version 13 and the chemical reaction. Those two are tightly bound together. We'll use some functions that are new since the last tech conference, namely like molecule name, find isomers. Let's see, in there we'll also see maximum common substructure, molecule align. Let's see, MoleculeMatchQ. We'll take a brief detour and explore the integration with the machine learning capabilities via feature space plot. And then we'll end up looking at a selection of resource functions that the chemistry team has added to the function repository. All right. Let's see. Yeah. So this is my timeline plot for chemistry in the Wolfram language. Let's see. Why not just show the details here, right? So in 2007, we had version 6.0 and we introduced chemical data. And then for a good period of time, chemical data was where you went to get information about curated information about chemical entities. And then over the intervening time, lots of different data functionalities were added to the Wolfram language. And so a new framework to kind of tie it all together was brought in, the entity framework. With entity value, chemical entities that came in version 10. And along with next came some integration with PubChem. And then starting in version 12, we had Molecule, let's see, what do we like to say? A first-class citizen of the language, right? So it's a Wolfram language data structure. It's a Wolfram language expression. It can be modified. You can create any kind of molecule, and that's what distinguishes it from the chemical entities. It doesn't already have to be stored in the database. And then since then, we've been expanding on that with import-export formats, MoleculeDraw, molecule name, molecule align. So that's where we are. What I need to add here now is when we introduced biosequence and some other capabilities. But okay, so that's the timeline plot there. Let's see. Right. So chemical data is fairly familiar, right? Or it's fairly old, right? So with chemical data, the way it works is you give it the name of a chemical and then the property you want, and you get that back. And so it was very a dedicated function. But then in version 10, we got chemical entities. And so now we start to have a representation, a language representation of a chemical. And so it's these little yellow boxes, as we like to call them, right? So if I take one here and I copy it and I convert it to its input form, we see it's really its entity chemical piperidine. If we evaluate that, it formats nicely in the notebook, but really it's the exact same. If you were to write it to disk, it's this format. So that's just so this is the underlying expression and this is the formatted box, right? So with entity value, you can pass in multiple entities, you can ask for multiple properties. And again here, just like the entities, these properties have a nice formatted form in your notebook so that they're pleasing on the eyes, but they have an input form that's very computable. So so you can write pattern matching to catch entity properties. You can construct these. Yeah, they're discoverable, right? So you can do entity properties chemical to get a list of them, just in the same way that you could do entity list of chemical, which I'm not going to evaluate right now because it's there's a lot of them, and it it does take a non-zero amount of time to generate these generate these formatted forms, right? So I'm not sure if this is maybe somebody could tell me in the chat. Do you guys see tooltips in the Zoom? Because that will come up later, right? So here, when you hover over one of these entity boxes, it gives you an idea of what's in there, right? And so, oh, wait, so what did I see here in the chat? Yes, excellent, thank you. Right, so that's chemical entities, and let's see, so that must be the end of the slide, and that's why it stopped scrolling. Excellent. So then in version 12, we brought in the molecule. And so you can create a molecule out of an entity if you want. You can create a molecule out of something that is most certainly an entity, right? So we certainly have water in our knowledge base, right? And but you can create that molecule. And if you look at its input form, it's very much like a graph. It's modeled on graph, right? So your first when this evaluates, the first argument turns into the list of atoms, followed by a list of bonds, followed by options, basically. Right. So so it's an atomic object, and that's kind of funny, right? So what does atom Q mean in the Wolfram language? It does not. Or let's see. So that's atom, and this is atom Q. So atom Q is a very old symbol. It's been in the language since a long time, and atom only came in version 12 for the molecule. And funny enough, an atom is not atom Q, but a molecule is atom Q. And so what that means is once it evaluates, the only way to get the stuff inside it is through the accessor functions. So we created this mol up here. We said mol equals molecule water. Well, that's interesting. Okay. Mol equals molecule water. I can ask for the first of that. And it's going to complain about a non-atomic expression. So I don't know why the screen flashes like that when I do an evaluation. But anyway, so that's why you don't use first to get the things inside. You use atom list, bond list. You use the property accessors. You can ask mol for its properties, and you'll get back a list of all of the different types of properties grouped in a convenient way. So you've got 3D descriptors, atom properties, right? So you can ask whether a particular atom is aromatic. You can ask for its chirality, all of these things, its molecular mass, adjacency matrix, and whatnot. And then there's a whole host of functions for editing and computing with the molecules. Right, so then now we have in version 12.2, we introduce MoleculeDraw. And so this is I hope this works well here in full screen. Let's go out of that and let's pull up MoleculeDraw. So the way that MoleculeDraw works is it pulls up a window. It blocks the kernel, and you are free to draw a molecule however you like. And so at this point, what's new in version 13 will be this button for drawing a carbon chain and for then adding rings to it. And then we can change which ring. We've got a few here. The plan is to make this into a grid with many more after the initial release. So we can choose to grab a cyclohexane ring and put that right here off of the benzene ring, and then we can return that. And so it returns it back to the session. And so probably that timed out or something for drawing that is the reason. Yeah. Okay. And so then also we have a function MoleculeRecognize that can take an image. And so you can grab an image from a PDF just using the little screenshot snippet tool, paste it into your notebook, and then let's see, edit it directly, right? So we can come here. So I can bring another benzene right out here. I can put a bond here. I can do the same here. Bond here. And it automatically interprets that correctly that those are aromatic and that the aromatic system, the conjugated pi electrons kind of extend over the whole molecule here. So we can return that. And now we can ask it for its name, actually. And this is new since the last tech conference. Molecule name queries available sources. So it calls the Wolfram Knowledge Base. It can call PubChem. It can call the NIH with their cactus chemical identity resolver. Let's see, I have another chat here. No, it's not machine. How does MoleculeRecognize work? It is, let's see, so it is basically old school OCR. It's not machine learning, as far as I know. It's open source, and so it's actually the MoleVec library that we're using under the hood there. So let's see, I need to move this guy. There we go. Right, so on to something new for version 13. This is something that GraphPlot has had for quite some time, but MoleculePlot has not, mainly because with molecules, we need to be able to place the labels in a decent position. So here, if we look, let's see, so you can make a molecule plot of water and tell it you want the atoms labeled by their index. And generally speaking, you care about the atom index when you need to do structural modifications on this. If you need to change an atom, right, you need to know what its index is, right? So if I wanted to do molecule modify of that mole, and then I want to set mass number of 1 goes to, let's see, oxygen, let's say it's 16, right? And that percent was actually a graphics there, so we don't need that. But that's why you would care about the atom index. Yep. And so in that case, I made an isotopic substitution on the molecule, and the atom indices on the plot helped me to do that. But you can also provide a list of rules and give individual labels to every atom. We have as well as atom index, there's another special string here. You can say atom chirality and get the traditional R and S labels on a molecule indicating the stereochemistry. And I believe, yeah, so there's actually a better example of that right here. So make a 2D plot of glucose and mannose, and put them in a column and label the stereochemistry so that you can understand. Obviously, this is only one form of these. This is the straight chain form versus the ring form of these sugars. But you can understand the difference between them. I mean, they're basically the same molecule, but it really depends on the 3D arrangement of these atoms. Let's go back and catch that example that I skipped. So we can make a plot of trinitrotoluene, and we can give the labels in a more specific way. We can give a pattern for the labels. That way I want any carbon or nitrogen to be labeled by their oxidation state. And so in this case, we see that nitrogen has a +3 oxidation state because it's giving up its electrons to the oxygen and the carbon here. Right, and so you can do that in 3D as well. So now go past this one that we already looked at. And we'll look at chemical formula, right? So the point of a chemical, well, here I wrote this out, why ignore it? So a chemical entity is a single chemical species with a record in the knowledge base, meaning that we have the people who work for Wolfram and Wolfram Alpha have curated, gone through data sources and curated properties and like melting point, specific heat capacity or whatnot. And so those are the entities in the knowledge base. You can create a molecule to represent any chemical or any molecule, right? And then so then the bounds are kind of off, but you lose access then to those curated properties. Well, so a chemical formula basically is only supposed to represent either any or all chemical species with a given formula. So if I tried to make a molecule and I just said C6H5OH, now it would be reasonable to assume that this is 1-hexanol or that this is phenol. But molecule isn't going to make that assumption because this isn't a computable input. It's not a name that can be converted, and it's not a SMILE string. So molecule doesn't know what to do with that. Chemical formula does. So a chemical formula basically, it's just a representation of a species with a given formula. So for just having the formula, you can know the molecular mass, you can know the net charge, you could get a list of all the elements in it, element counts. And you can also use it to see whether a particular molecule matches that. So MoleculeMatchQ, and here we have, so this is phenol, and we're giving it the formula. And it comes back as, let's see, let's get the little, yep, good, came back true. We're in a buggy phase, so if things don't work, I need to fix them. Right, so here's a silly example where we take something that is clearly not a real chemical, but just to kind of throw it at the chemical formula and see if it's able to parse this. So we just assemble a list of all the atomic symbols, and then we make a function to grab a random one and put it next to C2H4, and then give it a random subscript. And so we can convert that and create the chemical formula object. And so you can convert that to what's called the Hill form of a formula where, so in the Hill form, it's a standard form for a chemical formula. The carbons come first, hydrogens come second, and then all remaining atoms come in alphabetical order. And they only show up one time in the formula versus a more structural formula where you can have CH3, CH2, CH2, CH3. That doesn't work in a Hill formula. A Hill formula just has every element just once. So you can compute its molecular mass. And then you can also use a new function called find isomers. And that will not find any isomers with this particular formula. And so we're going to go over what find isomers does shortly. But I want to touch on MoleculeMatchQ. It's a new function in 13.0. It joins other pattern matching functions like find molecule substructure, molecule contains Q, molecule free Q is also new, molecule substructure count, right? So basically it's like a isomorphic graph Q when given two molecules, except it needs to make sure that the graphs are isomorphic and that the atoms and the bonds match each other. So it'll come back true if I put in two, the only difference between these two water molecule expressions is the order of their atom, and so it comes back true. You might remember, so let's see, molecule equivalent Q, and that is what is being deprecated by MoleculeMatchQ. Placed. All right. Because MoleculeMatchQ can do more. It can tell you not just are two molecule objects the same, do they represent the same molecule, but it can ask you, does this molecule match this formula? And it is true. you can test whether a molecule matches a pattern. And so in this case, you use a molecule pattern, and we're not going to go into exactly how to decode a smart string, but essentially what this means, this is a line notation. It's a shorthand that says this represents any 6-atom structure or substructure that is aromatic, and that's what a lowercase a means. And it's a ring because we see this 1 show up there twice. You'll have to take my word for that. Actually, it's got a nice formatting. Right. So MoleculeMatchQ of this molecule against this molecule pattern, and it will come back true. It's different than MoleculeContainsQ because MoleculeMatchQ requires that this pattern not only be contained by this molecule, but that every heavy atom, every non-hydrogen atom in the molecule has a match in the pattern. So it's distinctly different than a MoleculeContainsQ. You can also pass in a bond as the pattern. So hydrogen chloride matches against a bond with chlorine to anything. This is an interesting part of it. If you match 2 stereoisomers, L-alanine and D-alanine, then they'll come back false. But if you pass in the option to ignore stereochemistry, it comes in true. Same for isotopes. Water matched against heavy water comes in false. Water matched against heavy water with ignore isotopes goes to true, and it is a match. So, right. I just wanted to briefly show this, right? So we've got all of these different ways of representing the same thing. So I can make a biosequence with just one amino acid, and it's I'm going to find out later that that's threonine. So I might make a biosequence with just one letter. So it's a waste of biosequence, but the point here is that you can represent the same things at all these different levels. You can have a biosequence, you can convert that to a molecule, you can convert that to an entity, and you can convert that to a formula. These all are trying to represent the same thing, but at different levels, different information available. With the biosequence, you can take its complement. I don't know enough to know if that's a reasonable thing to say when talking about a peptide, but you can do translations to get the DNA that was needed to encode this peptide, things like that. With a molecule, you can generate 3D coordinates, you can generate 2D plots. With an entity, you can access the curated information, and likewise for the formula. And we just discussed the formula, I mean. And the point here, the reason this was in here, is that you can pass these things into MoleculeMatchQ. And if the first object represents a molecule and the second is a pattern or a formula, then it can return true or false. Right. So with the chemical formula, one of the main consumer functions for that is going to be called find isomers. So if let's see, right. So I already ran this one because it takes a second to run. So I called find isomers on C6H5OH, right? And so that was we remembered phenol, right? So phenol is the one that first comes back. So what this does is it calls the knowledge base and it calls PubChem basically to see if they have any molecules, any records matching that formula. And so phenol was the obvious one for that formula, such that I might have even thought that molecules should just take it and return that. But it's clearly not the only valid molecule expression with that formula. And again, this is not an exhaustive list. This was a lookup. This called PubChem for their records, and they have 99 million records, and so that's why they generally will return more than we will. Yeah, so that's why we found those isomers for phenol. You can also find, say specifically that you want entities, and so we have 2 in our knowledge base. You can also ask it for the SMILE string. So if I gave it something like C12H17NO2, it's a little bit easier to read if that's formatted, right? C12H17NO2, then we find that PubChem at least is able to return 19,000 molecules from that. And in that case, it's a lot easier if you just return them as smile strings and store them that way, because these can be converted to molecules very quickly and on the fly. There's no reason to store them, serialize them in the molecule form if you've got the smiles. Yeah. So here's a silly example to find all the isomers of 2-hexene and then make a word cloud out of the visualization. Right. This is a little bit more interesting, a little bit less silly. So we can find all the isomers of caffeine, and then we can filter them. So here we find all the isomers of caffeine. I wrapped that in echo so that we could see how many it found. It found 2,500. And then we can filter it by saying we want only those that contain this substructure. It's a bond between an aromatic oxygen atom and an aromatic nitrogen. So out of the 2,500 that it found, the ones that match the pattern there were only 252. And then we can take those, find a random sample of 5 of them, and find the maximum common substructure between those, right? And so that turned out to be this substructure. It's a little 5-membered ring with some things that are either, let's see, nitrogen or oxygen. Right, so no, reading smart strings is an art. I tell that I don't fully know, but regardless, so you can take those molecules that you found, you filtered out the ones that matched your pattern, you found the maximum common substructure between them, and now you can use that substructure as a highlight when you plot the molecules in 3D. So molecule maximum common substructure is new since last year's tech conference, as is molecule align. So we take all of these different molecules and we align them all using the MCS as a pattern. So essentially what you see here is this is showing all of the different, let's see, all of the different molecules in 3D laid on top of each other. And as you see, the only part that really matches is that 5-membered ring with the two little dangling hairs off of it. Let's see what was in the chat here. Right, I didn't think of, so a coffee filter, that's great. We found isomers of caffeine and then we filtered them. That's good, I like that. So now let's talk about chemical reaction. So chemical reaction is it's a representation of a reaction between the reactants and products. So we can feed it. The most natural way to create one would be to take a rule of associations. So we represent the reactants as entity goes to coefficient, entity goes to coefficient. This could also be a chemical formula or a molecule. And so it formats saying that we've got zinc hydroxide plus sulfuric acid goes to zinc sulfate plus 2 waters. If you hover over these, you get a clue about what's behind the formula. You've got accessors for the reactants and the products. You can get the counts because those are very useful. You can get a display equation. You can also create a reaction from an equation string, and these need to be written in a reasonable way. Put spaces around the pluses, spaces around the arrows. I mean, the former being much more important, so they're not confused for charges. You can also create a reaction from a reaction smiles string. Smiles strings are slightly more readable than smarts strings, but again, out of scope for this meeting to really go into what they are. But it is a line notation, a format to easily see, to represent the reactants and the products. And they're separated by this guy. And so that's what allows me, in writing this and parsing the strings, to easily see, does it have this to separate the left and the right? Then it must be a smiles. If not, then I'm going to treat it as an equation. Right, so I want to get to balancing equations because that's the most interesting thing that you can do with the reactions at the moment. So we can take your chemical reaction, and instead of passing in associations with the counts, we just pass in the entities. And so it still comes back as a reaction, but it's not balanced. And you can ask, are you balanced? And it says false. So then you can balance it. And it will come back, and in this case, it put a 2 in front of the water. That was the most interesting thing it could do there. It also takes charge into consideration, because if we look at this reaction, it's mass balanced. It's got one copper, one iron, one copper. So it's mass balanced, but it's not charge balanced. And so reaction balance Q says no. And then when you balance it, you see that it puts 3 in front of this copper and 3 in front of that copper. Hey, kappa. All right. Right. So then if you try and give it a reaction that can't be balanced, you'll get a reasonable message telling you that chlorine shows up on the left and not on the right. So you can't just substitute your one acid for another and then not change your salt. You can give it some more interesting reactions, and it should be able to balance them. And then, wow, okay, so I am out of time. Right, no, so Fe3 plus, I don't have a way to interpret. I would interpret that, at least the parser is going to interpret that as, so I didn't know if I repeated it. The question is Fe3 plus equivalent to Fe plus 3. And no, because it's going to interpret the 3 as a subscript in that case. So you could either enter Fe plus 3 or Fe plus plus plus. Yeah, and so that is, that's that. So there's some more slides, but they're mainly just examples that you can go over on your own. And so I am out of time. No, so it would be really nice if there were vibrational modes available. Yeah, but we do not have that. All right. Oh, I do not. So no. Is there a standalone parser? No. So essentially, chemical formula is its own parser. Yeah, so it's got, I mean, it takes it and it does a string replace and a string cases and all that good stuff under the hood. Thank you very much for your time.